Hello, everybody. Welcome back to Measure Theoretic Probability. In today's video, we're going to talk about the famed Borel-Cantelli Lemmas, and there's two of them. And generally, what these are about is we're going to have an infinite sequence of sets or events, A1, A2, A3. And for these theorems or lemmas, it's helpful to think of them as something that's occurring in like rounds of a game. Like maybe A1 is you win the first round, and A2 is you win the second round. And I think that's helpful for the interpretation of the Borel-Cantelli lemmas. And we're going to see under some conditions, we can guarantee that the probability that infinitely many of the events occurs is 1, or the probability that only finitely many is 1. I'll motivate that with a couple of examples. Let's get into it. I'm going to start with a probability space consisting of a non-empty set omega, a sigma field curly F, and a probability measure P. And this should be at the top of every slide or every theorem today. I just don't want to write it over and over again. So if you don't see any sigma field in what we're talking about, and suddenly I'm grabbing events or sets out of F, it's because there is one overarching sigma field for everything I want to talk about today. So let's start with Borel-Cantelli 1. I'm going to start off with an infinite sequence of sets or events, A1, A2, A3, out of the sigma field F. And I'm going to look at the sum of the individual probabilities. If that sum is finite, then I can say the probability of the lim sup event is 0. So we also call this event ANIO, which means that the AN occur infinitely often. I think this notation is, personally, I think it's misleading because when I see an N up here, and this N is shorthand for N goes to infinity. So ultimately, this entire event here does not depend on N, but I don't see that in this notation. So for me personally, I would like to put brackets around the AN here, but I'm not going to do it. I'm going to stick with the more typically used notation. So when you see PANIO, it's not something about the nth event. It has to do with the whole sequence. And you can interpret this as the event that infinitely many of these events from the sequence occur with probability 0. Equivalently, you can say that finitely many of the events occur with probability 1. Before proving Borel-Cantelli 1, let's look at an example. I want to play a game with you. And suppose the game is in rounds. Actually, I don't want to play this with you. I don't have enough money. So someone's playing a game with you, and there are rounds of the game. In each round, you are going to bet 2 to the n dollars, or whatever your unit of currency is. Now, already this sounds really scary to me because as the rounds progress, you are betting a lot of money. This 2 to the n is blowing up. But suppose you win a round with probability 2 to the n over 2 to the n plus 1. And when you do, you net $1. So you get back your 2 to the n plus an additional $1. And with the rest of the probability, you lose your 2 to the n dollars. That sounds even more scary to me because although you have a larger probability of winning, and by the way, this probability is going to 1 as n goes to infinity. So each round, you're more and more likely to win, yet you're only winning $1 at a time. And you have, in lower rounds, a very high probability of losing all your money. Should you play this game? For those of you thinking of a martingale, this is not a martingale, but it is closely related. Now, if you don't know what I'm talking about there, I don't want to do the tangent right now. We'll talk about martingales in here eventually. Is this a fair game? Your expected winnings on each trial, you expect to gain $1 with probability 2 to the n over 2 to the n plus 1, and you expect to lose or gain negative 2 to the n dollars with the rest of the probability. And when you add this up, you get 0. So it's fair in that sense that each round of the game, you don't have a negative expected winnings, which is true of most games in casinos, except for craps if you play the odds on your bets. I'm going to define AN to be the event that I lose on the nth trial. Then the probability that AN occurs is 1 over 2 to the n plus 1. Note that the sum over n of 1 over 2 to the n plus 1 is a little bit difficult, but if I make the denominator smaller, I have terms that are bigger. So it's a larger sum when I look at 1 over 2 to the n, and you probably don't have to rewrite this, but I'm going to rewrite this as the sum of 1/2 all to the n, and this is a nice geometric sum. The sum as n goes from 1 to infinity of r to the n is r over 1 minus r as long as r is in magnitude less than 1. So this is 1/2 over 1 minus 1/2, which is 1, which is pretty darn finite. So we are set up for Borel-Cantelli Lemma 1. we do have that the sum of the probabilities is finite. Borel-Cantelli 1 tells us that the probability that infinitely many of the events occur is 0. So this is saying the probability that you lose infinitely often is 0, which is saying that you will only lose a finite number of times with probability 1. That sounds like a pretty good game to me. The catch being you need to be able to stay in it and keep putting up more and more money, much like a martingale. If we keep playing this game, we will eventually get to +1, +1, +1, +1 out in the limit, and our total winnings is going to go to infinity. So there's an application of the Borel-Cantelli Lemma 1. Maybe you could guess this, because we had the probability of winning getting larger and larger and the probability of losing getting smaller and smaller. But there is always a positive probability of losing on every trial. So maybe you didn't guess this, or maybe you believed that this result should be true, but how do you show it? This is how you show it. Let's get to the proof. Suppose that we have these events A1, A2, A3 on up, and the sum of the probabilities is finite. This implies that tail sums. So if I sum as n goes from like m to infinity, and I let m get larger and larger, these tail sums have to be shrinking to 0. Otherwise, the original infinite sequence couldn't converge. We want to show the probability of an infinitely often, or the lim sup of the an. We want to show that that probability is 0. So let's write out what the lim sup is in terms of intersections and unions. Note that we are intersecting sets like this as n is changing. And if you keep intersecting sets, you get things smaller and smaller than any one of the individual sets that you're intersecting. In other words, this intersection set, is contained in this set for any particular n greater than or equal to 1. It doesn't matter what n is, you're eventually going to hit it in the intersection, and that intersection is going to be contained in that set for that particular n. So I can use monotonicity of the probability measure to say that this probability is less than or equal to the probability of just this event occurring. And again, this holds for any n greater than or equal to 1. I would love to get that union out of there. I don't know that these events are disjoint. So I can't use countable additivity of a probability measure, but I can use countable subadditivity, which doesn't require that they're disjoint. So by countable subadditivity, the probability of this union is less than or equal to the sum of the individual probabilities. This looks like something we've seen before. Maybe the letters are different. The indexes might be changing here. But we do know that these sort of tail sums of these probabilities goes to 0, as in this case, this n goes to infinity. So let's go back to the beginning. The probability of the lim sup is a number that this does not depend on n, because this over here is shorthand for the lim sup as n goes to infinity. So the result coming out of this should not depend on n. It also doesn't depend on m or k or anything like that. Can you take the limit as n goes to infinity of the sequence, real numbers, little a1, little a2, little a3, if they're all the number 3, as n goes to infinity, nothing's changing, and the limit is 3. So the limit is not affecting at constant sequence. So maybe that was a difficult way to say that this is, if I take the limit of this expression as m goes to infinity, or really any other letter, I'm looking at the same number over and over and over again, and so that limit doesn't really change anything. In other words, this probability is equal to this limit of that probability. This is like a sequence of some probability, like 0.8, 0.8, 0.8, 0.8. And so that limit is equal to the original individual value. We did show on the previous slide that this probability here is less than or equal to the sum. I have to change the letters so that the indices don't quite match the previous slide. The sum as k goes from m to infinity of the probability that ak occurs. Believe me, I spent a lot of time thinking about the best way to use these indices and the changing letters, and I didn't come up with a best way. I came up with what I thought was the least confusing way. I tried this many other ways. But remember, the limits of these tail sums is 0. So up here, I've got the probability of the lim sup being less than or equal to 0. Probability can't be negative, which forces this probability to equal 0. That's exactly what we wanted to show. So we are done proving the first Borel-Cantelli lemma. Borel-Cantelli lemma 2. I'm going to start out looking the same way. I've got an infinite sequence of sets or events, A1, A2 on up. I'm going to look at the sum of the probabilities. Now before, that sum had to be finite, and now it's infinite. And I would love to just go to the punchline here about a lim sup or maybe a lim inf. but I'm going to need another condition here to get the result that Borel and Cantelli were going for. So if this sum is infinite and the events are independent, then I can say the probability of the lim sup event is now 1. This is the same thing as saying the probability that infinitely many of the events occur is 1. So if this was maybe the events like you're winning on a round of a game, you are going to win infinitely many times. So if this is like events like kind of like before, actually the opposite, we had AN being losing around. If AN is winning around, then you will win an infinite number of times if you can stay in the game forever. Before proving this, I have a couple of things we're going to need. The first, and you may know this already, and if you didn't, it may feel completely reasonable to you, but I think it's just a little bit tricky to show, is if events A1 and A2 are independent, then the complements of those events are independent. So to show this, I want to look at the probability of the intersection of these two complements, and I'd like to see that this is the product of these individual probabilities. I'm going to use De Morgan's laws to write this probability of A1 complement intersect A2 complement as the probability of A1 union A2 all complement. And then I've got the probability of a complement. So this is 1 minus the probability of that union. I could keep pushing forward until I get the desired result, but I think this is a little easier personally to come at it now from the other side. So on the other hand, that's what this stands for. Let's look at the probability of A1 complement times the probability of A2 complement. And let's write each of these out as the 1 minus probabilities that they are. I'm going to multiply this out to get an expression here. And I don't know if you see it. Let me take out this negative. Does this expression look familiar to you? Remember the probability of a union. Imagine a Venn diagram and having two sets with potential overlap. The union is all the area in there. And you can get it from the area of one of the sets plus the area of the other, but you've double counted the intersection, so you need to remove it. This is, in fact, one expression out of many for the probability of A1 union A2. And that's what we had up here. So we have that this is equal to this. And we have proved that independence of A1 and A2 implies independence of the complements of A1 and A2. The second thing we're going to need is an inequality. So I claim that the expression 1 minus x is less than or equal to e to the minus x as long as e is not negative. When I see something like this, the first thing I think of is the Taylor or Maclaurin series expansion for e to the minus x. I can write it as 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial, etc. And here's the 1 minus x. So if I want this to be less than this, that means I want all of this to be greater than or equal to 0. Or equal to 0, I guess would work here. But I think it's kind of hard to show that this is greater than or equal to 0. So I'm not going to use this. I know I wrote it, but this is the first thing I think of when I see something like this. Instead, let's graph the function e to the minus x and y equals 1 minus x. The way I've graphed it here, it doesn't appear that there's any sort of intersection in here. But I guess there could be if you really zoom in on the picture here. Can I say that this line is always below this curve when x is greater than or equal to 0? This line, y equals 1 minus x, is in fact the tangent line at the point 0, 1. It's the tangent line of the function e to the minus x. To see that, let f of x be e to the minus x, take a derivative, plug in 0, you get a slope of negative 1. The equation of the line going through this point, x equals 0, y equals 1, with a slope of negative 1, is the line y equals 1 minus x. And because e to the minus x is a convex function, or concave up if you prefer, we know that if you look at a tangent line, that tangent line has to stay below the function. That's what we wanted to prove. We are now ready to go for the Borel-Cantelli Lemma Part 2 proof. Here's a quick recap. We have events or sets A1, A2 on up from a sigma field F. We've got that the sum of the individual probabilities is infinite and the AN are independent. And we want to show the probability of the lim sup event happening is 1. And you can translate this as saying infinitely many of these events, as you keep running through time, infinitely many of these events are going to occur with probability 1. To start this proof, I want to make the notation a little more compact. So I'm going to use a capital A to denote the lim sup, which is the intersection as n goes from 1 to infinity of the union as m goes from n to infinity of the AM. In this proof, I am going to have some indices flipping around, which is a little confusing. So this is, of course, equal to the intersection as m goes from 1 to infinity of the union as, say, k goes from m to infinity of the ak. So those sorts of things might happen in this proof a couple of times. Now, since A is the lim sup and we want to show the probability of the lim sup occurring is 1, we want to show the probability of A occurring is 1. But I think it's a little easier and equivalent, certainly, to show the probability that A complement occurs is 0. That's what I'm going to go for. And the first thing I'm going to do is write out A complement in terms of these unions and intersections using De Morgan's laws. Now we're ready to take the probability of, I was going to say this, but I actually don't want to go there yet. I just want to look at these like so-called tail intersections. So I want to look at intersections of events from some number up to infinity. And I'm going to flip the letters here, so stay calm. For any fixed n, if you look at the intersection as m goes from n to infinity of the am, let's look at that probability. This is an intersection of events that are independent using property 1 of those things we showed right before the proof. If the A's are independent, then the A complements are independent. But I can't break this apart into a product of probabilities because we can only talk about independence of an infinite number of events or sets through finite subcollections. So this infinite intersection is a little bit troublesome, but note that the more things you intersect, the smaller your set gets. So I can say that this whole probability by monotonicity of probability is less than or equal to the probability of a smaller intersection starting from n and stopping at some k, where k is greater than or equal to n. Again, that's because this set is contained in this set. Now I can use independence to pull that intersection out as a product. And now I've got probabilities of complements of events. So I'm going to write those or rewrite them as 1 minus probabilities of the original events. Now here is just a number. It happens to be non-negative. This is my 1 minus x for that hint. I can say that 1 minus x in this case is less than or equal to e to the minus x, where this is x. So I've got that this whole expression is less than or equal to the product of these e's, e to the negative probability of am. And if you multiply a bunch of terms like this, you get e to the sum. And again, this will hold for any n once that's fixed, as long as k is greater than or equal to n. So we just showed this, and I want to use this to find this probability. Note that this probability is dependent on n, but it's not dependent on m because that's just an index that's running over a bunch of values. I'm using the same kind of thing I did in the previous proof where I'm taking a limit of constant numbers because what I'm trying to say is this does not depend on another letter like k. Let's use k. And so this probability is equal to the limit as k goes to infinity of the same probability. It's like the sequence 3, 3, 3, 3, 3, not changing as the index changes, and we're taking the limit and getting the original 3. Using the line above, we know that this is less than or equal to the limit as k goes to infinity of e to the negative sum as m goes from n to k of the probability of a sub m occurring. As k goes to infinity, this k up here is going off to infinity. So I'm looking at an infinite sum. Even though I'm starting at some n, I still have an infinite number of terms as k goes to infinity, and this sum is going to diverge to infinity. We said that the full sum diverges to infinity. All you need to do is take out some numbers between 0 and 1 up to the point n, and that's not going to change whether or not this converges or diverges. You would have to be careful with a statement like this if you had some kind of canceling series, like a telescoping series, where you take part of it and it goes off to infinity and the other part goes to negative infinity. You might have a problem there. But here, we're just dropping a finite number of finite terms. And if the full sum to infinity diverges, then this tail sum will as well. So just like in the previous proof, we've showed that a certain probability is less than or equal to 0. And because a probability is not negative, that implies that the probability is equal to 0. So let's go back to the set we care about. I want to look at the probability of A complement that is written as a union of an intersection of the individual AM complements. I'm going to take that union out. It doesn't just come out because I don't have disjoint sets, but I can use countable subadditivity to say that this is less than or equal to the sum as n goes from 1 to infinity of the intersection as m goes from n to infinity of the p am complement. But this is 0. I mean exactly 0. I don't need a limit. We showed it right here. Here's where we got the result that this is 0. So we're summing a bunch of zeros, and that's just 0, and we're done. We've showed that the probability of a complement is less than or equal to 0. That forces it to equal 0, and that's what we wanted to show in Borel-Cantelli 2. As a quick example, let's start a sequence of infinite trials where we're independently flipping a p coin. What I mean by this is you've got two sides like heads and tails, and heads comes up with some probability p, and tails comes up with the rest of the probability. In general, with a statement like this, I would need p to be between 0 and 1 inclusive, but for my example, I need it to be strictly between 0 and 1. I'm going to let an be the event that the nth flip is heads. Now the ans are independent because we're flipping the coin independently each time. And the sum of the probabilities of the a's is the sum of a bunch of p's. Even though this is small, it's not decreasing. We're adding a constant over and over and over again, and that constant is greater than 0. So this sum is blowing up. So I've got independence and the sum of the probabilities diverging. We can use Borel-Cantelli 2 to say the probability of the lim sup event is 1. And this can be interpreted as heads will happen infinitely often with probability 1, which I'm sure you're not surprised about. Flipping a coin that has some positive probability of coming up heads forever, you're going to see heads infinitely many times. Let's do the same example again, but make it a little more interesting. Let's consider a run of 10 million heads in a row. I claim that we've basically just shown that we're going to see runs of 10 million heads in a row infinitely many times. And I guess academically, that seems reasonable because it's just kind of an extension of what we just did, but that also seems bizarre at the same time. That's a lot of things to line up a whole lot of times. So let's start out by letting an be the event that the nth flip was heads. This is not going to take us anywhere, at least with Borel-Cantelli 2. We can't do this because we have lots of overlapping things. The first 10 million and then the second one from that batch all the way out to the 10 million and 10 million one. We've got these overlapping events. And so the ans are not independent, which is why I'm going to define them a little bit differently. To get rid of this problem, I'm going to start looking at non-overlapping blocks of flips. So let's consider flips 1 through 10 million, and then 10 million and 1 through 20 million and 1, and then 20 million and 2 through 30 million and 2, etc. And let's let an be the event that the nth block is all heads. So because they're non-overlapping, I do now have independent events. Seems like a big waste of information, but this is going to get us there because now we have, again, independent events. The probability that an occurs as the probability you see 10 million heads in a row in 10 million flips, and that is p to the 10 million, which is really small, but not 0. And so the sum of these probabilities is infinite because I'm just summing a constant, a very small constant, but we do need, it's not sufficient, but necessary that our terms in the sum are going down to 0, and they're not here. So I've got independent events, and I've got a divergent sum of the probabilities. We can use Borel-Cantelli 2 to say probability of the lim sup event, or that the an events occur infinitely often, is 1. And that translates to we are going to see blocks of 10 million heads. We're going to see runs of 10 million heads infinitely many times. And we're not even going to have to look at overlapping runs. We may get many more heads in there, but we're going to see full, complete disjoint runs of heads, 10 million of them, infinitely many times. So as I was saying before, if you look at the first example, there's probably no reason for you to think otherwise here, but I certainly don't feel that this is intuitive. Or maybe I do, but how do you show it? Here's how you show it with Borel-Cantelli Lemma 2. So that's it for today. In the next video, we're going to talk about tail events. That's going to be kind of like what we talked about today. We're going to have infinite sequences of events from sigma fields, and we're going to look at the events from some point out to infinity, like we did today, some fixed point out to infinity. And we're going to look at intersections of such things and sigma fields generated by such things. And I can't convince you right now why you care about that. It would be too much of an aside. I hope to convince you in the next video. We're also going to hit Kolmogorov's 0-1 law. So I hope you come back. And if you do, I will see you in the next one.